Right, folks, let's get started. It's a pleasure to introduce George Saon. George is at IBM. He's in the speech recognition group. They used to have a superhuman speech recognition effort going on, and I don't know if it's still called that, but he's part of that team.
The advanced LVCSR.
So now they're called advanced LVCSR. Okay.
We're more modest.
And George comes to us from IBM, but before that he studied in France. And my French is not great, so you'll have to pardon my pronunciation, but he was at the Henry Poincaré University, which is up in Nancy. I think the French are somehow in love with mathematicians. They seem to name a lot of things after them. And before that, he was from Romania, and he's now here. And he and his team, of a couple of other people who you might hear from later in the semester, did some great work and were the best placed team last year in the year's conversational speech evaluation. And so we decided we'll call them over one by one and have them tell us all the deep secrets of their system. You already heard last semester from Dan Coley, and this time back to you, George.
Thank you, Sanjeev, so much. So I'm part of the advanced LVCSR research, like Sanjeev said, which is, again, a group in the human language technologies. And I'm going to talk today about two ideas that we used in the last year's evaluation. One which is related to speaker adaptation, and it's a nonlinear feature space transformation technique. And the second item on the outline is precision matrix modeling, and most particularly I'll talk about full covariance matrix modeling for LVCSR, and I'll put it in the context of various other covariance modeling techniques, such as extended maximum likelihood linear transforms and subspace precision and mean transforms and mixtures of inverse covariances. Okay, so for the first item, the idea behind nonlinear feature space transforms is that in principle they have more potential than linear transforms, especially so if you take speech that was recorded in a car at 60 miles per hour. So the characteristics of the features for that speech are highly different than, say, clean speech. And to give you an idea why nonlinear transforms have more potential is, for instance, when you use MLLR, if you use a regression class-based MLLR, so you use multiple MLLR transforms, you usually cannot outperform a single linear transform. So this points to the fact that nonlinear transforms have some hope. Also, we will see that these techniques, they don't require first-pass decoding, which is a big advantage if you operate under tight time constraints. So we can apply them in a totally unsupervised manner. And also, you can look at these nonlinear transforms as a higher-order version of Kepstrel mean and variance normalization. But instead of stopping at the first and second order moment normalizations, we go all the way up to higher order moments. And these transforms come in the context of some related work done by Scott Chen and Ramesh Gopinath, which was published in NIPS 2000, and the CDF matching algorithm, which was introduced by Satya Dharani-Pragada and Mukund Padmanabhan in ICSLP 2000 as well. So let's start with CDF matching adaptation. We defined the cumulative distribution function of a random variable x as the probability that the realization of x is less or equal than lowercase x. And this is simply the integral from minus infinity to lowercase x of the PDF of the random variable x. Now we can approximate capital F of x by what's called the empirical CDF. So given n capital N training samples from x1 to xn, the empirical CDF of x is 1 over n summation from 1 to the number of samples of this step function evaluated in x minus xi. So I wish I could draw somewhere. Basically, if you have CDF of a random variable like here, every time you encounter a sample, you take 1 over n, a step of 1 over n on the ordinate axis, okay? And so now the idea of this technique is to match the test CDF to the training data CDF, okay? So here's an example. I hope everybody can see this green line here in the back. So here's an example. We picked a particular dimension of our feature vector for some years data and plotted the training CDF in red for that dimension and the test CDF in green. So what we want to do with this technique, we want to superpose the two distribution functions. Okay. So we want to map the test CDF in green to the training CDF in red. So how do we do that? Well, first let's notice that the empirical CDF is simply the rank evaluated in one of the samples, is the rank of that sample in that sorted list of samples divided by the number of samples. Okay? So if you go back to the previous formula, I'm sorry. Here the number of non-zero terms in the summation is the number of samples that are greater than xi, actually. Okay. So let's denote by A the set of the adaptation data, x1 to xn, and the associated empirical test CDF, and by T the training data, y1 to ym, and the empirical training CDF with capital G subscript m. So this transformation is a mapping from the adaptation data to the training data given by the following composition. We take the inverse CDF of the training data and apply it to the CDF of the test data. Okay? And this has the property that the CDF, if you compute the CDF on the test data, then it will be the same as the CDF of the mapped sample of the training data. So maybe this is not clear. Let's go back to, on this picture it's a lot easier to explain. What we do here, we take each sample of the test data, we look up its CDF value, then we map it to a sample of the training data which has the same CDF value. Okay? I'm sorry. Now, what if instead of mapping the CDF of the test data to the CDF of the training data, what if we map it to the CDF of a predefined distribution? And in particular, what if we pick the target CDF to be a Gaussian distribution function? So this is called a Gaussianization transform. And the idea is that if you have a random variable capital X, you want to find a transform capital T such that the random variable capital Y is normally distributed. Okay? And we make this simplifying assumption that the dimensions of X, so assume X and Y are both vectors of random variables, we make the assumption that the dimensions are statistically independent. And I'll talk later on about ways to cope with the problem of statistical independence. Okay. And here we have the standard normal PDF and CDF. And we, as I said, we want to map the random variable X to the random variable Y, which has the PDF phi of X and the CDF capital phi of X. Okay. Okay, so how do we do that? Again, let the cumulative density function of capital X be capital F, defined like before. And let's start, instead of giving you the direct result of this mapping, let's try to derive it. So then we ask the question, what is the transformation such that if I apply it to my random variable X, the divergence between the distribution of the transformed random variable Y and the CDF of a normal random variable is minimized? In particular, how do I find T such that this distribution is 0? So now what we have to do first is we want to relate the probability of the PDF of capital X evaluated in some point to the PDF of the transformed variable in the Y, okay, evaluated in the image of the transformation. So instead of T inverse of Y, think of it as lowercase x. It will be easier to follow. And the two are related through this equality where this term here is the absolute value of the Jacobian of the transformation. which in the case of one-dimensional transforms is simply the derivative of the transformation. Okay? So, divergence is minimized when the two distributions are pointwise the same. So we say that lower phi of y has to be the same as p as the probability of the random variable y evaluated in lowercase y, which from the previous slide we can relate to the probability in the original space of the random variable x. Okay? So now what we do to that equation, we integrate it from minus infinity to t hat of x, where t hat is the transform that we look for. Okay? And then by a simple substitution rule, we get this equation here, which says capital phi, or the normal CDF evaluated in the image through t of x, has to be the CDF of x. Okay? Or otherwise said, since phi is, we can invert this transformation, we have the transform t that we're looking for is the composition between the inverse normal CDF evaluated in the CDF of x, which is exactly the same result as we had before for the CDF matching, if you remember. Okay? Okay, so here's a simple example. We started out with a distribution. Again, we picked randomly one dimension of our feature vectors on the year's data, and we plotted the distribution of that dimension, which looks, well, it has this shape, I guess. It looks more like a Laplacian distribution. And then after we apply this transform, of course, the result is a Gaussian distribution. And on the next slide, we have we plot the actual transformation t, which corresponded to that mapping. So just to give you an idea of how such a transform looks like. And one thing to note is that all this transformation, whether it's a Gaussianization transformation or a CDF matching transformation, they're all monotonically increasing. And actually, you can, there's a dual solution to the problem. You can also find transformations which are monotonically decreasing, which satisfy that the property that the divergence has to be minimized. You can just map, instead of mapping lower valued sample to higher valued Gaussian samples and so on. You can just revert the sign at some point. Okay? So some results. Now the first set of results was published in our ICAST 2004 paper, so they're slightly outdated. And we compared systems trained with maximum likelihood and minimum phone error. And as you can see, we get 0.4% on the maximum likelihood and slightly more, 0.6% on the minimum phone error models. And we observe the same phenomenon if we look at more recent systems, namely full covariance models that we trained that were recent. Here again, we see slightly more gains if the systems are trained discriminatively, 0.6 versus again 0.4. And some very recent results obtained on Arabic broadcast news, RTO4 data set. So we did some work in preparation for the Gale evaluation on this set of systems. And here we compare systems trained with FMLLR or SAT trained systems with and systems on which we apply MLLR on top. And here we observe some really nice gains of 1.9% on the SAT systems and of 1.6% if we add MLLR on top of it, which is a pretty sizable gain. Okay, so unless you have, sure.
So in the full covariance models,
Yes.
you're still doing the Gaussianization per component.
Yes.
Okay.
Yes.
You're not worrying, you're not trying to make the cross terms independent like you do later on.
No, especially for full covariance, there's no need to do that. And we actually, if your original space has the property that the dimensions are independent, then after Gaussianization, that property seems to,
yes.
It's not guaranteed to hold, but it seems to hold in practice.
Another quick clarification. So in the plots that you showed earlier of one dimension, obviously certain sounds like silences and others are going to dominate the distribution. So you probably just remove those plots are without silences, I suppose.
So that's a very good point. We actually don't remove the silence. And
Yeah.
there is a paper by Herman Nye and company where they looked at explicitly enforcing a certain percentage of silence in that CDF matching computation.
Also, they downweighted.
Yes, they downweighted or upweighted silence to make sure that the ratio of silence to speech is the same in training and test. However, when we tried it, we saw no gains. But that could be because we naturally had the same amount of silence in training and test because of our segmentation, the way we trained our segmenter on the test data. So it could be more important for some other, if you have a mismatch in the amount of silence, yes. Okay, so next I'm going to move to the second part, which is about precision matrix modeling. Again, precision is an inverse covariance matrix, just to make sure we're on the same level with the terms. So first I'm going to show some geometric interpretations of some problems with currently used diagonal covariance models. And then I'm going to talk about two ideas that were developed at IBM, which try to cope with these shortcomings. One which is called extended maximum likelihood linear transform, which builds on the work of Ramesh Gopinath on MLLT, and Mark Gales on what he calls semi-tight covariance transform, which is actually exactly identical to MLLT. And the second refinement of these techniques is called subspace precision and mean, SPAM, or mixtures of inverse covariances. It was proposed independently by Scott Axelrod from IBM and Vincent Van Hoek from, and Anant Shankar from, where is he now? At Nuance? At Nuance, yes. And then I'm going to talk more in detail about our work, or in our group, on full covariance modeling for LVCSR. So it's a continuum of techniques, if you want, from diagonal covariance models all the way up to full covariance models. Okay. Now this is a simple picture. What it says is that if you have a cluster of data that's skewed in your feature space, then you have to cover it. You have to spend a lot of mixture components to cover that region, because the diagonal covariance Gaussians have the property that the hyperellipsoids, if you want, of equal likelihood, are axis parallel. Okay, so if you have a skewed cluster, you have to spend a lot of mixture components. Whereas if I were to apply a transformation, a simple rotation to this cluster, then I can spend a single mixture component to model the cluster accurately. Does this make sense to everybody? The second problem is closely related. It says if you have two clusters which are skewed, say sigma 1 and sigma 2, and you model them with diagonal covariance models, then you have an area of misclassification here due to the incorrect covariance modeling assumption. If I were to model these two clusters with full covariance models, then the area of misclassification will be almost zero in this example. And again, in this case, what one can do is apply a simple rotation such that both ellipsoids are axis parallel, in which case you can model them accurately with diagonal covariance. So what can we do about these problems? So the first idea is called extended maximum likelihood linear transforms, or EMLLT. And it says that take the precision matrices and model them as capital A, lambda I, capital A transpose, where lambda I is a diagonal matrix which has a higher dimension than Pi. It has a dimension capital N by capital N. And A is a rectangular matrix which has a smaller number of columns than a smaller number of rows than a number of columns. So what this model says is that you can think of your PIs as being a projection from some higher dimensional space of some diagonal covariance models into the lower dimensional space by denoted by lower class, whose dimension is lower class n. Okay, or the other way to look at it is you take some full covariance models in the lower dimensional space, and you apply an immersion of these models into a higher dimensional space, such that in the higher dimensional space you can represent them with diagonal covariance. Okay, that's one way to look at it. Now there's two special cases for capital N. At the left, when the dimensions of the two spaces are the same, we have the semi-tight covariance transform, or also called MLLT, depending on whether it's the Gale's terminology or the Gopinath terminology. And in this case, A is simply a rotation in the same space. It's actually a general affine transform, but think of it as a rotation. The other extreme is when capital N reaches this bound here, n times n plus 1 divided by 2, meaning that the number of diagonal entries in lambda I is the same as the number of full covariance entries, or the number of free parameters is the same as the number of full covariance matrix. So in this case, we practically reach full covariance modeling complexity, meaning that the actual A here doesn't matter anymore. You can put any A you want. If you have n times n plus 1 divided by 2 diagonal entries, then you practically can model any full covariance. Okay. So now there's an improvement to this technique called subspace precision and mean and MIC. Like I said, introduced by Axelrod and Van Hook. And the idea is this. So let's rewrite the MLLT equation as a summation over the diagonal entries, lambdas, and the rank 1 matrix. So this rank 1 matrix is formed by taking the columns of the A matrix and multiplying by its transpose. Okay? So Aj is a column vector, like I said, of lowercase n times 1. And we have capital N such column vectors. Okay, and capital N linear coefficients in front of those rank 1 matrices. So let's call this rank 1 matrix Sj, capital Sj. And then we have that if you have an EMLLT model, then Sj is a rank 1 matrix. Of course, it's Aj times Aj transpose. Now what SPAM and MIC do, they say, let's remove the constraint that Sj be a rank 1 matrix. Let's have the Sj be a general matrix. So that's, and it simply says that let's choose Sj such that the result, the Pi that we're interested in, are symmetric positive definite matrices. So that's the generalization that happens in SPAM and MIC. Or otherwise, another way to look at it is these Sj's will define a basis in your n squared dimensional space. You have capital N elements of that basis. Okay? And then you represent each precision matrix Pi as a linear combination of those basis vectors. Okay, so what about if we go all the way and try to do full covariance acoustic modeling? So the motivation that we started from was that we have, in full covariance acoustic modeling, we have even fewer assumptions than any of the previous models. The other idea is that we couldn't train full covariance acoustic models for a long time because we didn't have enough training data to reliably estimate those matrices. But nowadays, it happens that on the English CTS task, we have 2,300 hours of training data. So suddenly, it became, at least in principle, possible to train a full covariance model for LVCSR. The other reason that we had is, again, to improve performance. We wanted a system which committed different types of errors compared to our diagonal covariance system. So we thought that having a system where the output distributions are modeled by full covariance Gaussians will be complementary to a diagonal covariance system. And the fourth item, we just wanted to show that it's actually feasible. So to dispel the myth that it's impossible to train such a system. But then we had to overcome some challenges. So the first one was how to build the initial models. The second one, which is actually much more important, is how to speed up the actual likelihood computation. And third was how to do discriminative training with full covariance models. And fourth was how to do adaptation. So for getting the initial full covariance models, what we did is we used Viterbi state alignment of the training data with a high resolution diagonal covariance model. And by high resolution, I mean a model which had something like 850,000 mixture components. Then we took the same model and we clustered it to a lower resolution diagonal covariance model, something like 143,000 mixture components.
So in both the cases, the clustered states were the same?
Yes, yes. The number of states and the decision tree didn't change at all. It's only the number of Gaussians per state that changed. Then we accumulated, based on the fixed alignment provided by the higher resolution system, we accumulated full covariance statistics for each of the individual low resolution diagonal covariance mixtures. And then we took, so now you get a full covariance model, seed model. And then we refined the training of that model by doing standard forward, backward, and MMI training. So this is in contrast to some other schemes where you, something that LIMSI, I think, tried to do, where they tried to grow the full covariance model from starting with 1 Gaussian per state up to the final number of Gaussians per state, which is more costly in terms of compute time. So the way we dealt with the likelihood computation, we applied 2 ideas here. The first one was hierarchical clustering. So you take the means and the on-diagonal variances of the full covariance model, and you cluster them again to 2,000, something like 2,000 mixture components. And then at runtime, you only evaluate the full covariance Gaussians which map to one of the top n clusters. So you evaluate all the clusters at each time frame and then select the top n, say 100. And then evaluate only those Gaussians which map to one of those clusters. And it's important because here we use only the on-diagonal variances, or the top level is given by a diagonal covariance model. So it's important to operate in a MLLT feature space, or in a feature space where the covariances are mostly diagonal anyway. And the second idea that we used is the Cholesky factorization of the precision matrices. So we wrote each sigma inverse as C transpose C. And then when you compute likelihoods, you have to evaluate expressions of the form X transpose sigma inverse X. And this you can expand as a sum over your dimensions of a dot product between row Ci of the Cholesky matrix and the feature vector X squared. Okay? So this is a sum of squares, meaning that you can threshold, you can bail out of the computation as soon as this partial sum exceeds a threshold. You don't have to evaluate the entire sum up to the number of dimensions. Okay. So we used those 2 ideas for speeding up the likelihood computation. And now about MMI training. So at IBM we use something called implicit lattice maximum mutual information training. So it's implicit in the sense that we never write out those lattices to disk. So the way it works is we compile a static decoding graph like we would do for normal decoding, except that we use a much weaker language model, such as a unigram, and we don't put the word labels in a graph. And then we run forward backward on that graph instead of Viterbi. So what this gives you, it gives you a state posterior at each time frame. And when you multiply that state posterior with the normalized mixture likelihoods, then you get a Gaussian component posterior at each time frame. And that's exactly what you need to accumulate the MMI statistics. Okay. So here I gave a couple of advantages. So it's relatively fast, although it's of course slower than if you had the lattice explicitly written to disk. But it's the big advantage is the memory efficiency. You don't have to store lattices on disk for 2,300 hours. Okay, and that saves you something like 100 gigabyte. So that's quite significant. And then you don't have I/O overhead, and you can also argue that it's more correct because the dominant paths or the lattice is recomputed after each update of your models. Okay, so the MMI equations that we used are fairly standard, at least for the means and the variances. So instead of having mu ij squared like you would have for diagonal covariance models, you just have outer products of means here, and you subtract the outer product of the re-estimated mean. But now there's an interesting problem. You want to choose the d, that famous MMI constant, such that the re-estimated covariance is positive definite. Now this is an easy problem if you have diagonal covariance models, because you'll end up with one-dimensional inequalities basically that you just quadratic inequalities that are easy to solve. But what do you do in this matrix setup? And it turns out that you have to solve a quadratic eigenvalue problem to find the optimal d. And so there are methods to do that. You can actually treat a quadratic eigenvalue problem of dimension n as a linear eigenvalue problem of dimension n squared. So there are ways, but what we did in practice, we didn't do any of that. We simply increased the value of d until we saw that the sigmas were positive definite.
Where does the sigma come in this equation?
Excuse me?
Where does the sigma come in this equation?
Okay, so sigma I is here, hat, right? You want sigma I to be positive definite. Now sigma I depends on d here, here, and here, because mu I hat depends on d as well. And when you do an outer product on these guys, then you have a d squared. Okay, so that's all. Yes, I'm just, so yeah, it's just a shortcut for actual coefficients. Okay, the other thing with these discriminative training techniques is smoothing is very important. It can make or break the discriminative training of your models. And it's doubly important if you use full covariance models, because of that sensitive nature of having matrices well conditioned and so on. So we use two forms of smoothing, one which is called I-smoothing, introduced by Dan and Phil Woodland in 2002, which says that you can add a certain number of artificial counts to the mean statistics, the variance statistics, and the count statistic, denoted by tau. So those are, you just add them artificially to the various counts. And the second type of smoothing is the off-diagonal element variance smoothing, where you divide the off-diagonal elements by a factor which is proportional to the, I'm sorry, what's the best way to put it? Let's put it this way. If the ML counts for that particular Gaussians are high, then you don't do anything. You leave the off-diagonal elements unchanged. However, if that Gaussian gets very few ML counts, then you divide the off-diagonal elements by this expression here. So this new term here starts to dominate. Okay. In particular, if it gets 0 counts, then you'll just zero out the off-diagonal elements. Okay. So some results with the MMI for full covariance. First, the runtime. So we can decode in 3.5 times real time using these models without loss in accuracy. The MMI training takes 1 times real time for the denominator statistics, which is the computationally intensive part. And to give you an idea, so on 2,300 hours of data, it took us about 3 days to run 1 iteration of MMI. And now the results. So here we compare 3 different systems. They're all full covariance systems, and they're all the same size. The only difference here is the feature space in which those models were trained. So the baseline feature space is the FMLR SAT, which comes on top of VTLN, LDA, MLLT. Then here we have a Gaussianized feature space on top of SAT. And here we apply FMP, which is the transform that Dan talked about a couple of months ago, on top of, again, the baseline feature space. And we see gains for MMI in the range of 1.1% to 1.4% for the FMP features. And if we compare directly the performance of 143K full covariance system versus 850K diagonal covariance system, it's not quite a fair comparison. Because if you compute the number of free parameters, the full covariance system has 30% more free parameters. But we see something like 0.6% improvement at the ML level. And this improvement tends to go away, unfortunately, once you do MMI. Somehow our procedure for doing discriminative training for diagonal covariance models is much more efficient yet. Okay. So the adaptation, that will be actually my last slide, I guess. So there's 2 forms of adaptation. Actually, there's more than 2, but the linear transform type of adaptations. So for FMLR, which is the feature space transform, there's no problem because we estimate the FMLR transform using a different set of models. We don't use the full covariance models for the transform. And for MLLR, we make again, a very simplifying assumption. We treat the full covariance model as a diagonal covariance model by stripping out the off-diagonal elements. Okay, and like I said before, it all depends in what feature space you operate. If you operate in an MLLT feature space where the dimensions are decorrelated, then you can get away with this approximation. And here I show some results on cross adaptation, or just 2-pass adaptation, where we take the output of the speaker-independent system to estimate the transforms of the full covariance models. And of course, the gains are relatively huge, but there's a lot more going on. I mean, there's a lot of hidden gains which are not explicit in this table. But we can compare here. So how much we lose if we do self-adaptation? So we lose 0.5% by using the output of the SI system here. And here if you use the SI system is, again, almost 1% absolute loss compared to using a much better system to provide the adaptation script. And I will finish with this, and the only slide is a list of references for people on these various techniques. So thank you for your attention. If you have any questions or no.
So in Gaussianization, you did 2 kinds of Gaussianization. One was matching the test CDF to the training CDF, and the other was matching normalizing both CDFs to unit.
Right. To a Gaussian CDF, yes.
Right, Gaussian CDF. So did you show numbers for both types?
No, I didn't show. Now I can.
Are they different, or how different are they?
Yes, I would say Gaussianization helps more. But not by much. So on the years data, if you remember the gains, actually I can put them back up. So the gains on the years data were small, between 0.4 and 0.6. And with the CDF matching, you get gains in the same, between 0.2 and 0.4, I would say. However, we didn't do it on the Arabic broadcast news data. But intuitively, we expect the Gaussianization to be better because it forces, if you think a little about it, it does some sort of speaker adaptive training. I mean, you would achieve the same effect with the CDF matching if you were to apply the warping on the training speakers as well. The point in Gaussianization is that the training speakers are mapped as well as the test speaker, whereas this is not done on the CDF matching.
Similar to SAT.
Yes, it's a form of a nonlinear SAT.
But it could be anything. It doesn't have to be Gaussian.
Yes, it could be anything. But again, so yeah, so I tried the Laplacian distribution just for fun, and the results were actually slightly worse than. So somehow it does matter what target distribution you put there. I mean, it's really easy. The Gaussianization is implemented as a table lookup. You just type in MATLAB norm in for,
Right.
then you get a full table of inverse normal CDF values, and then that's it. And then you just sort your samples, and you look up the corresponding entry in the table. And
Yeah, intuitively, since you're using mixtures, and there are all these other things that happen, state clustered mixtures and so on, it's not very intuitive why Gaussian should do better. It seems like it should simply match. That's all should matter.
yes, I agree. There's no reason why we should. Well, there is. Let me go here a little. Where is it? There is a slight reason. So if you look at these two distributions, they're pretty much Gaussian. If I were to plot a CDF of a Gaussian, it will look very much like these two distributions. So you want your transform, the effort on the transform, to be as small as possible. You don't want to warp, things unexpectedly. So that could be a reason. Yeah, sure.
One more question. So in the script that you showed for doing full covariance, bringing up a full covariance system, you mentioned LVC has a bottom-up full covariance trained system right from get-go, and it's more expensive, but how does it compare in accuracy? Does it give you a better gain, or do you know the number?
So we don't know, because we did not do the experiments the way they did it.
I mean, do they have better gains than you have in the full
No, they abandoned the full covariance system because they didn't see gains over a similarly sized diagonal covariance system. So the story, yeah, it's like I said, if you do MMI, then the gains, the benefit of using full covariance may go away. However, we did use it in the evaluation because it provided a complementary system for cross adaptation. And we got something like 0.3, 0.4% by using the full covariance system as the output of the full covariance system as input to our best FMP diagonal covariance system. So we tried all possible inputs for that system, and the full covariance gave the best results. So it was useful in that sense, I guess.
Good slide where you had the results for the full covariance, and you had a couple of notes at the bottom. I didn't catch that because the thought that I was trying to resolve in my mind. No, one more.
Yes, here.
Is that, in some sense, if you have a diagonal covariance system but with more Gaussians, you are somehow trying to cover the same space with, placing more Gaussians around it. So, and of course, with diagonal covariance, you have less computation to do. So in some
Well,
sense,
it's not obvious. If you have to spend a lot more mixture components, then you have to evaluate a lot more.
right. So what I'm saying is that in some sense, the two systems really are comparable. So in the sense, both in terms of computation.
Complexity, yes, I agree.
Sort of trade.
Yes.
Whatever computation I need for the full covariance, I'll add more diagonal Gaussians so that
Right.
I get comparable computation and then
Right.
and have the same footprint in the probability.
But not in terms of what they model. I mean, even adding a lot of mixture components, you don't model the shape of the distribution is not the same as having a single
Right.
full covariance model.
Well, that's assuming the data is Gaussian, because once
Yes,
it's not
yes.
Gaussian, it's better to model it with a mixture of Gaussians than with a single full covariance
True.
Gaussian.
True.
So I'm trying to figure out where the things stand. So I thought that maybe these nodes had something to do with it.
No,
And
these
yes,
nodes
we
simply
figure
tell
out-
you what happens if you change instead of the SI script, if you use a better adaptation script, how these numbers change.
Oh, I see. I
But
see.
they're not really
Okay, so
relevant
this is
to-
only to do with, okay.
Yes.
Because no, the reason
yeah.
I even thought about what I just said is because of the way you initialize your full covariance system. You
Mhm.
essentially take a diagonal covariance system
Right.
with many more Gaussians. and you
Right,
just-
but then you cluster it. I mean,
So, so when
Yeah.
you're done clustering, what I would say is that you have created a density which has a footprint which is not axis parallel by combining these things.
Right.
And that's the density now that you want to model as a full covariance Gaussian. So I would say that I think you gave a comparison which is actually quite fair, but I would compare that system with the full covariance system. And
I see.
maybe that's what you said was over there, because you said there was an 850K Gaussian system with a full covariance.
right, right. So the
Full
850.
covariance had a few more parameters.
Yes.
But at the point where you switched from this diagonal to the full covariance, you added those parameters in order to try and cover
Yes. Yes.
density.
They're only covariance parameter. Yeah.
Okay,
So,
I think that answers my question. So I thought this had something to do with it, but I guess not. Okay. So this simply
Yes.
says if you have a better SI system somehow,
Yes. Yes.
then
Or some
after-
other system then. So,
Okay.
yeah, so what I wanted to say, what I didn't show in this table is how much you gain if you do self-adaptation on the full covariance systems. And it's about 1%.
Okay.
And that's perfectly in line with what you get using another. If I were to use a non-full covariance system, I would get the same thing by doing self-adaptation. So that's how we validated that making that approximation of treating the full covariance as a diagonal covariance for adaptation was okay in terms. We
There's
didn't.
one question though which the full covariance leaves out, which is that when you do adaptation at test time, when you now have more parameters to adapt. So if you're dealing
No,
with short
but
speakers like-
that's what I'm saying. You don't have more parameters to adapt because you strip off you don't do variance adaptation. You strip off the off-diagonal elements and you do only mean adaptation.
Oh,
So,
okay, sorry.
so in effect, it's like having a small DC system that you're adapting.
Okay. Well, that's what it means to say with self-adaptation.
Yes.
Okay,
Yeah.
sorry. Okay,
Mm.
I didn't. Okay, now it's making more sense. Okay. And you haven't looked into some sort of map-like adaptation of the full
No,
covariance?
no. Actually, we sort of abandoned the full covariance work. Maybe we should get back to it because we didn't see clear gains except in a cross adaptation setup of using full covariance. So.
One more question on the EMLRT thing. So you said EMLRT can range from having n small n basis matrix to all the way to n times n plus 1 by 2.
Right.
So what's a good operating point in terms of trading off?
That's a good question. So if I remember, again, this is based on Peter's work and Ramesh and Scott. So I think their most efficient operating point was like something 4 times lowercase n, 4n. So they always try to double 2n, 4n, and 8. And the best trade-off was around 4n, I think, for their tasks. It may be completely different for yours. It's an interesting, the whole genealogy of these transforms is pretty interesting. So it started way back with some paper by Shukat Talamazini or something, who actually came up with the first form of STC and HLDA. Because what I didn't say is that STC and MLLTs are forms of HLDA when you don't project, but use a full rank transformation. And then it diverged into sort of Nagendra Kumar's work on HLDA and then Mark Gales' work on STC. And then Ramesh came up with the MLLT, which is the same as STC. And then at IBM, we extended from MLLT to eMLLT and SPAM and so on. So it's a nice tree of transforms. Mm.
Let's thank our speaker again.